Hey guys, this tutorial is going to focus on the concept of the buoyant force, and we're going to actually look at some of the more complex problems that you could see. And we got Jerry here, a little rubber ducky, and he's going to be with us for this first example. Before we jump into the first example, however, I want to just recap what buoyancy is. So here we have it. The buoyant force is equal to the weight of the fluid displaced by an object in fluid. So this is Archimedes' principle, and he noticed that buoyancy, or the buoyant force, is actually equal to, if you were to take the weight of the fluid that's displaced by an object and you were to weigh it, that would be equal to the buoyant force. So there we have it, and our formula is buoyant force, symbolized FB, is equal to the density of the fluid times the volume displaced, or underwater, times gravity. That's just a quick reminder to get us to move forward here. So, let's jump into some of the more complex problems that you might see dealing with buoyant force. Well, looks like Jerry had one too many Girl Scout cookies, but let's see what we can find out about this problem. So Jerry, who has a mass of 94,300 kilograms, is floating in the bay. If the area of Jerry's base is 115 meters squared, and the density of the water is 1,025 kilograms per meters cubed, what is the height displaced by Jerry? So that's asking how much water, if we were to see, like, if we could measure the height that is displaced by Jerry, what would that be? So we're not really talking about volume displaced, we're talking about just the height of the volume. So let's go ahead and write down givens and a free body diagram. So if you want to pause the video, you can go ahead and try that, and then we'll get going. All right, so this is a free body diagram and the given. So our free body diagram, we should have the buoyant force, which is pushing up on Jerry, and the weight of the earth acting on Jerry. Our givens, we have the area of the base, which we could kind of assume is like a big circular base. And so that's not our volume, that's just the area. So, whoops, looks like this should be squared. There we go. And then we have the density of the water, and we are looking for the height displaced. So what formula do you think would even come close to dealing with height displaced? Like, where would we even go to find that? Well, let's look at our buoyant force and weight formulas that we know and see if there's anything that we can kind of unravel there. So for buoyancy, we have density of the fluid times volume displaced times gravity, and for the weight of the object, we know that that equals density times volume of the object, which actually is the mass, times gravity. Luckily, we have the mass, which was given, the 94,300 kilograms, so we could just multiply that by gravity to get our weight. And you may have been thinking this, but to find height displaced, it's probably going to be hidden in the volume displaced. So if you were thinking that, great job. So let's go ahead and figure out how we can find volume displaced, because we know volume is area times height, and that will probably help us to find height displaced. So I just brought this formula right down here, and we got buoyant force, density of the fluid, volume displaced, gravity. Now the problem, we have the density of the fluid, we know gravity, but we don't know buoyant force yet, and we don't know the volume displaced. So we have to find buoyancy. Any idea of another avenue to find buoyancy? Hopefully you said that the buoyant force is equal to the weight based on the fact that Jerry is floating on the water, and so his buoyant force is equal to his weight, because if it wasn't, he would be accelerating up or down. So at this point, I'm just going to plug everything in now that I know that my buoyant force is equal to my weight. So the weight, which is also buoyancy, is 943,000 newtons, is equal to the density of the fluid times our unknown right now times gravity. And just keep in mind, we're trying to find height displaced, but we have to find volume displaced first. So when we do the algebra, we get the volume displaced is 92 meters cubed. And I'll just remind you that volume is simply area times height. And in this case, since we're talking about the volume displaced, it's going to be the area of the base, which we're given, times height displaced, or height underwater. And that's what we're looking for. So I'm going to make this a little smaller, just so we have more room. And now we can actually plug in the area of the base, which was 115 times the height displaced, and we come out with 0.8 meters is Jerry's height displaced, which means that that's how much height is underwater. So I know that was kind of a lot, so if you need to pause the video and kind of write it down or rewatch it just to get it down, again, we were going for that height displaced, and this one was tricky because there's no formula that we know that magically has height displaced. But if we look into what we know that buoyant force deals with volume displaced, and that's our key to get there. So then we had to go and we had to remember that we can use our free body diagram and know that buoyancy is equal to weight, and then we were able to solve the problem. So great job if you were able to follow along, and let's jump into another complex problem that you might see. Okay, so this one's a little bit different. We see that in the bottom right we have a picture, and the picture is going to be described here. So a cork here is held down in fresh water by a spring right there. If the cork has a density of 612 kilograms per meters cubed, and the volume of the cork is 0.03 meters cubed, what is the magnitude of tension on the cork by the spring? So you might be thinking, whoa, we're trying to find tension now? I thought we were on buoyancy. Well, it's kind of cool because we can combine some of the units that we've done, and we're going to be able to use our knowledge of buoyancy to actually solve for something new in the buoyant force unit, tension. If something were held down, or if we wanted to suspend something in water the opposite way, we could also do that. But let's focus on this problem. So I want you to pause the video, write down your givens, draw a free body diagram. Now be careful here because the cork is being held down, but it's also at rest. So think about what that means with the free body diagram. Pause the video and try both these two tasks. Okie dokie. So let's start with the givens. We're given the cork, the density of the cork is 612, volume of the cork is 0.03 meters cubed. The density of the water, we know it's fresh water, so that's how I knew it was 1,000. Now volume displaced, any idea of what volume displaced would be? Are we given it? Do we have to find that? Some of you may have thought about this, but the whole thing is underwater. So the volume displaced is equal to the volume of the cork because the whole thing is submerged. So volume displaced is also 0.03 meters cubed. So from now on, anytime the object is fully submerged, we know that the volume of the object and the volume that's displaced is the same. So let's look over at the free body diagram. We should have had weight and buoyancy, which we've been doing in the past couple classes. However, they're not equal here because the tension is actually holding it down. So if we were to cut the string or release the cork, it would float to the top because the buoyant force is greater than the weight, because we know that the cork is not as dense, so it's going to float to the top. So hopefully you got this free body diagram right. If you didn't, make sure you fix it before moving on. Okay, so how are we going to find tension? Well, we can actually set up an equation using this free body diagram because we know that the cork is at rest, and so this is balanced, this whole system, as far as forces go. So I'm going to set up an equation. I know that the buoyant force is equal to the weight plus the tension. So, and I got that from my free body diagram. It's the ups equal the two downs added together. Now I'm actually going to write out the formula for everything I know the formula for. So I'm going to actually break each of these down into anything that it can be broken down into. So I know that buoyant force is equal to density of the fluid times volume displaced times gravity. That's equal to, and I know that weight is density of the object times volume total times gravity, which is just a fancy expression for mass times gravity. And tension I'm going to leave because that's what I'm trying to find. So I want you to pause the video, and I want you to plug everything that you know in, and then I want you to try to solve for tension. Go ahead. All right, let's check it out. So here's my work. We got 1,000 for density of the fluid, volume displaced, and volume total are the same. We got gravity. We have the density of the object at gravity again, and then we have plus tension. So everything stayed the same. I'd plugged everything in. And then I get 300 equals 183.6 newtons plus tension, and I solve for tension. So this may have seemed like way out of your league, but if you were able to follow along, that is the first step, and that is really good actually. So you're going to get more opportunities to practice more problems like this, but this was just the start. So watch this as many times as you want, and thank you guys for watching.